All right, let's get right into it with a fascinating little puzzle that seems incredibly simple on the surface, but has this really surprising twist that's all about the physics of rotation. So picture this. You've got these three objects at the top of a ramp: a solid ball, a hollow ball, and a ring. They all weigh the same, they're all the same size, we let them go at the exact same moment. So, who wins the race? What's your first guess?
Your first instinct, and mine too probably, is to say it's a tie, right? I mean, they have the same mass, they're starting from the same height, so they've got the same amount of potential energy to work with. It just makes sense that all finish at the same time.
But, and this is where it gets really interesting, that gut instinct is totally wrong. And the reason why it's wrong, well, that uncovers a super cool concept in physics. Turns out there's this kind of hidden energy cost that we're not thinking about.
Okay, so to figure this out, we've really got to dig in and see what's actually going on as these things roll down, because it's not as simple as just sliding.
And that's the absolute key right there. They aren't just sliding down the ramp like a block of ice. They're rolling. And that means you've got two different things happening at once. The whole object is moving forward, and it's spinning around.
So why does that matter? Well, if you have two kinds of motion, that means you have to account for two kinds of kinetic energy. It's not just about forward speed anymore.
First up, you've got the one we all know and love: translational kinetic energy. That's just the energy of moving forward, from the top of the ramp to the bottom. It's all about mass and how fast you're going. But because they're spinning, there's this other kind of energy in the mix. It's called rotational kinetic energy. And honestly, this is where the whole mystery gets solved. It's all about the energy tied up in the spin. And what's really neat is that you can think about these two types of energy in a very similar way. They're like parallel concepts, which makes it a bit easier to wrap your head around. So check this out. For regular forward motion, we have mass, right? It's how much something resists being pushed. Well, for spinning, there's a rotational version of that called rotational inertia. It's basically a measure of how stubborn an object is when you try to spin it.
And that right there is the heart of the whole puzzle. If these things were just sliding, yeah, mass would be the only thing that matters. But since they're rolling, this other thing, rotational inertia, suddenly becomes the star of the show.
Okay, so let's talk about this rotational inertia. What is it really? And why is it the key to figuring out who wins our race? Well, it all comes down to shape.
Yeah, you can really just think of it as an object's stubbornness to rotate. And the wild part is, it doesn't depend on how heavy the object is. It depends on where that weight is. Is it all bunched up in the middle, or is it spread out to the edges? Think about a figure skater. When they pull their arms in tight to their body, they spin super fast, right? That's because their mass is concentrated near the center, giving them a low rotational inertia. It's easy to spin, but if they stick their arms out, their mass is far from the center, giving them high rotational inertia. It gets a lot harder to spin.
All right, let's bring this back to our racers. The solid sphere, the hollow sphere, and the ring. They all have the same mass, but their shapes are totally different. So let's look at how they spend their energy.
Okay, remember, they all start with the same energy budget. Think of it like a fixed amount of cash, and they have to spend that cash on two things: moving forward, that's the speed, and spinning as they go.
So let's look at the lineup. The ring, all of its mass is way out on the edge, as far from the center as it can get. That gives it the highest rotational inertia. It's the most stubborn of the bunch. At the other end, you have the solid sphere. Its mass is spread throughout, so it has the lowest rotational inertia. It's the easiest to get spinning. Now look at the ring's energy budget. Because it's so darn stubborn about spinning, it has to use a massive chunk of its energy, a full 50%, just on the act of rotating. That only leaves half of its energy for actually moving forward and winning the race.
But then you've got the solid sphere. It's not stubborn at all, it's easy to get it spinning. So it spends way less energy on rotation, only about 29%. And that means it has a whopping 71% of its energy left over to pour into pure, unadulterated forward speed.
Once you see the energy breakdown like that, the winner becomes obvious, right? It's going to be the one that's the most efficient, the one that wastes the least energy on spinning and saves the most for speed.
So let's just walk through it. The solid sphere has the lowest rotational inertia because its mass is closest to the center. That means it spends the least amount of energy on just spinning. And because of that, it has the most energy left over for translational speed. It just accelerates faster. It's that simple.
So the solid sphere wins. It just cruises down to the finish line first. After that comes the hollow sphere, and pulling up in last place is our poor ring, which just spent way too much of its energy budget simply trying to get itself to rotate.
It's just a perfect example of how some hidden principle in physics, in this case the energy cost of rotation, can totally flip the result you'd expect. It really makes you wonder, doesn't it? What other races out there are being decided by these invisible factors?